Okay, so let's get into our trigonometric functions. One of the things you need to understand is that these trig functions are based off of a right triangle. That's extremely important to know. These trig functions are based off of a right triangle. If you don't have a right triangle, you can't use your trig functions like you are going to use them here. Okay? So we have 6 trig functions. Some of you may be familiar with them, some of you may not. And I'm going to put them in this particular order. I have cosine, sine, and tangent. Those are my 3 main trig functions. Now, the other 3 trig functions are reciprocals of these first 3. These 3 trig functions are reciprocals of these 3 over here, of cosine, sine, and sine. Now, one of the things that helped me to remember was that cosine and sine start with a C and an S. Secant and cosecant start with a C and an S. What I remembered, if I wanted to remember the reciprocal of cosine, since cosine starts with a C, its reciprocal did not start with a C, it started with an S. So cosine and secant are reciprocals of each other. Sine and cosecant are reciprocals of each other. The C's and the S's go together. Are you with me? If you're trying to find a way to remember the reciprocal of each other, the C's and the S's go together. Now, tangent, its reciprocal is cotangent. That's an easy one to remember because the reciprocal of tangent has the word tangent in it, so that makes it really easy. Okay, so let's find how we determine the trig functions of each of these particular, the value of each of these particular trig functions. So, if I want to find the cosine, and this is the abbreviation for cosine of theta, here's my theta. The side right next to theta is known as the adjacent side. The side opposite theta is the opposite side, and this side has its own special name. That's always called the hypotenuse, right? Okay, so if I wanted to find the value of the cosine of theta, then I'm going to take the side adjacent to theta and divide it by its hypotenuse. Sine. The abbreviation for sine looks like this. So the sine of theta. And yes, it's still pronounced sine. Now the sine of theta, to find its value, I'm going to take the opposite side and divide by the hypotenuse. And last but not least, tangent. The abbreviation for tangent looks like this. And to find the value for the tangent of theta, I'm going to look at theta and I'm going to take the side opposite theta and divide by the adjacent side. Cool? Okay, now, these 3 should be very easy to find because these 3 are the reciprocals of the ones we just found. So, which trig function is the reciprocal of cosine? Correct, secant. So the abbreviation for secant looks like this. So the secant of theta is just the reciprocal of cosine. So that would mean the hypotenuse divided by the adjacent side. Cosecant. Cosecant is the reciprocal of, correct, sine. Remember, the C's and the S's go together. Cosecant's abbreviation looks like this. So if cosecant is the reciprocal of sine, that means I'm going to take the hypotenuse and divide it by the opposite side. And last but not least, cotangent. Here's your abbreviation for cotangent. Since that is the reciprocal of tangent, I'm going to take the adjacent side over the opposite side. Cool? Okay. Now, this is how you find the 6 trig functions when you're talking about a right triangle. And then what we do later is we actually take a right triangle and we place it on that circle. And when we do that, how we find these 6 trig functions changes a little bit. So hang in there, I'll be right back. Okay, so here are my 6 trig functions again. And this is how you find each of these trig functions when you are on a right triangle, just like we discussed a few minutes ago. But sometimes we take that right triangle and we put it on this XY axis grid system. Are you with me? Now, when you take a right triangle and you put it on this grid system, the one thing that's extremely important is this. The initial side needs to be on the positive side of the x-axis. The triangle needs to be in standard position. And the theta that you're working with is always at the origin. So when I take a triangle and I put it on this grid system, here is my angle that I'm talking about. And theta has to be at the origin. And then my right angle is literally on the x-axis. Cool? When you draw your right triangle, your right angle is literally on the x-axis. And yes, it could be over here on the negative side as well, but for right now, let's just talk about leaving it here. So theta is at the origin. Now, couple of things. The side next to theta was called the adjacent side, wasn't it? Well, since that adjacent side lies on the x-axis, it's going to be known as x. The side opposite theta was known as the opposite side when it was just the right triangle. But this opposite side parallels the y-axis, so it will be called y. Now the hypotenuse. This one is a little bit different. It's not known as the hypotenuse, okay? It is known, and here's why, it is known as the radius. And you're like, well, why is that? Because literally, I can take this grid system, this XY axis, and I can draw a circle, can't I? That includes this triangle. And the hypotenuse of this triangle could literally be considered the radius of the circle. Cool? Okay, so now let's look at our 6 trig functions. If I'm on a circle, my cosine is now found by, instead of the adjacent side that's known as x, isn't it? Instead of the hypotenuse is known as r, isn't it? So your cosine is found by doing x over r. The sine function, you're taking the sine of theta. When it was just the right triangle, it was the opposite over the hypotenuse. Well, the opposite side, when you put it on this grid system, is now known as y, and the hypotenuse is known as r, so when you find it, it's y over r. Are you with me? Getting the hang of it? To find the tangent, tangent was the opposite side over the adjacent when it was just the right triangle over here. But as soon as you put it on the grid system, my opposite side now has the value of y, and my adjacent side is x. Cool? Okay, so over here, the reciprocals, the reciprocal of secant is cosine, isn't it? So this would be r over x. Agreed? The reciprocal of cosecant is sine, isn't it? So that would be r over y. And last but not least, the reciprocal of cotangent is tangent. So that's x over y. By the way, clearly none of these denominators can be equal to 0. So none of these x, y's, or r's could be 0. Or the hypotenuse, the adjacents, the opposite, none of them can be equal to 0. If they are equal to 0, we don't have a triangle anyway, do we? Okay. By the way, one note to yourself is that the radius is always a positive number. Just like the hypotenuse, whether you realize it or not, the hypotenuse of a right triangle was always a positive number. The radius of a circle is also a positive number. Cool? Okay. I got one other one other item to complete our chart, because I'm kind of making us a little chart here. The other item that sometimes this right triangle gets put on, sometimes it just gets put on a circle, as we have here. And sometimes it's put on what's called a unit circle. And you have to know what the word unit means. The word unit means one. So if it's on a unit circle, that means that the radius of the circle is equal to 1. Got it? Unit means 1. Unit circle means the radius equals 1. So, if we're on a unit circle, it's not x over r anymore. Since r is 1, cosine would just be x. With me? Sine of theta. Well, when it's on a regular circle, it's y over r. But if you are looking at it on a unit circle, r is 1, which means it's y over 1, or just y. Tangent of theta was y over x on a regular circle. Well, it's still y over x because I don't have an r in here. Got it? Okay. So secant. So since we're on a unit circle, secant would just be 1 over x, wouldn't it? Cosecant would be 1 over y, and cotangent would be still x over y. There's no r there at all. Does this make sense? Okay. Something else I'd like you to realize, with a right triangle always goes Pythagorean's theorem, doesn't it? And Pythagorean's theorem says a squared plus b squared equals, that's right. The Pythagorean theorem says a squared plus b squared equals c squared, where c is the hypotenuse. Well, when you put this on a circle, I don't have a, b's, and c's anymore. I have x, y's, and r's. And the one variable you need to identify correctly is the hypotenuse. And what took the place of the hypotenuse here? What's in place of our c? Yeah, that's r. So now it's equal to r squared. A and B are x and y, and it doesn't really matter which one you put first, but I just put it as alphabetical order. So Pythagorean's theorem gets adjusted a little bit based upon the variables. So now Pythagorean's theorem, when you have a right triangle on a circle, it's x squared plus y squared equals r squared. Cool? Okay, so hang in there. I got some special triangles for us to talk about. Okay, so let's talk about a 45 degree, 90 degree triangle. Now, one advantage we have for this particular triangle is, first off, I have a 45 degree right triangle. Okay, this is also known as an isosceles right triangle. Back from your geometry days, isosceles means two angles have the same measurement, which means their opposite sides have the same measurement. So for instance, if this side measured 5, then this side would also be 5, wouldn't it? So how would you find the hypotenuse for it? Yep, Pythagorean's theorem, which means you'd have 5 squared plus 5 squared equals c squared, right? So what, 25 plus 25 is? Good, 50 equals c squared. And no, stay off your calculators. I want to find the square root of 50, which means, isn't that just 25 times 2? And if I take the square root of 25 times 2, isn't that 5 square root of 2 equaling the hypotenuse? By the way, that's plus and minus, isn't it? But the hypotenuse is always positive. So that's a positive 5 square root of 2, wouldn't it be? Yeah, you have to remember how to take the square root without a calculator for non-perfect numbers. Good? Okay, so what happens if your 5 was now an 8? So that means the other side is an 8, isn't it? Which means now I have 8 squared plus 8 squared equaling c squared, right? So what do we have? 64 plus 64? equaling c squared. What is that? Whoops, put an extra square where there wasn't needed. Let's get rid of it. That's what, 128 is c squared? Square root it? Yep, plus and minus. Square root of 128. Isn't that just 64 times 2? So that's what you're taking the square root of. So isn't that just 8 square root of 2? And it has to be positive because it's a hypotenuse, right? I could go on like this all day with you guys, and you're going to see that there's a pattern, right? So here's the deal. To make our life simpler, what we say is this. We look at our isosceles right triangle, and to make things extremely simple for ourselves, let me put the 45 degrees where they belong. To make things simple for ourselves, we say each side is 1, which means the hypotenuse would be 1 square root of 2, wouldn't it? Because isn't that what was happening over here? Yeah, it was. Good. So now, let's look at those trig functions. This triangle becomes one of our friends. All right? This triangle becomes one of our friends. And I'm just looking at a right triangle, not on a circle. Okay? So if I'm looking at this right triangle and I have not placed it on a circle, that means you need to think adjacents, opposites, and hypotenuses. Are you with me? Adjacents, opposites, opposite, and hypotenuse. So let's get our 6 trig functions down here. And okay, so let's look at this 45, 45, 90 degree triangle again. We've decided that we're going to make things simple on ourselves, and we're going to make both the legs of the triangle a 1. And when we used Pythagorean's theorem, we realized it was 1 square root of 2, right? Just from the previous examples that we've done. Now, let's look at the 6 trig functions for this particular triangle. So we're going to look at the cosine of a 45 degree angle. Now, here's the thing. Do you think it matters which 45 degree angle I look at? No, it doesn't, because it's going to get the same answer either way. So now I'm dealing with a right triangle. So what do I need to think about? Adjacents, opposites, and hypotenuses? Or do I think about x, y's, and r's? Correct. Since it's just a right triangle, not on a grid system, not near a circle, we think of adjacent, opposite, and hypotenuse. So cosine is the adjacent over the hypotenuse, isn't it? So if I look at this 45 degree angle, adjacent is 1, hypotenuse is the square root of 2. If I look at this 45 degree angle, adjacent is 1, hypotenuse is square root of 2. So it doesn't really matter, does it? Now, here's the thing we need to remember. Are we allowed to leave a square root in the denominator? Nope. So we have to do what is called rationalizing. And if you're like, oh my gosh, how do you do that? Well, remember, since this is a fraction, I'm going to multiply the denominator and the numerator by the same number. I want to get rid of that square root out of the denominator. And the only way to get rid of a square root is by multiplying it by another square root. So, what do you think we'd multiply by? The square root of? Good, 2. You multiply it by itself, right? And in the denominator, you would just end up with a 2, wouldn't you? And if it worked for the denominator, we'd do the same thing to the numerator, which means the cosine of a 45 degree angle is the square root of 2 over 2. Cool? Okay, let's look at the sine now. Let's look at sine of a 45 degree angle. Sine is opposite over hypotenuse. So, I'm just going to circle the 45 degree angle I'm looking at, even though we said it doesn't really matter which one, because we'll get the same answer. So sine is opposite over hypotenuse. So it's 1 over the square root of 2, isn't it? Gee, that looks familiar. That looked just like the cosine. So here's the thing. You know you're going to have to rationalize it. It's going to happen the same way, which means we end up with the sine of 45 degrees being the square root of 2 over 2, just like the cosine. And it really shouldn't surprise us because since both legs have the exact same measurement, I should get the same answer for sine and cosine of a 45-degree angle. Good? Okay, go with tangent. Tangent is, that's right, tangent is opposite over adjacent. So that's 1 over 1, which is just, 1. All right, time to get the other three trig functions down. So what's the reciprocal of cosine? Good, secant. Starts with an S. So I'm looking for the secant of a 45-degree angle. Now, secant being the reciprocal of cosine, if I know what cosine is, I know what secant is, don't I? Cosine was adjacent over hypotenuse. So secant's going to be hypotenuse over adjacent, which would be the square root of 2 over 1, which would just be the square root of 2, wouldn't it? Okay. What's the reciprocal of sine? Good. Cosecant of a 45-degree angle. Sine is opposite over hypotenuse, which means cosecant is hypotenuse over opposite. So, no surprise, I get the exact same answer, don't I? Reciprocal of tangent? Good. Cotangent. So the cotangent of a 45-degree angle. Tangent is opposite over adjacent, which means cotangent is adjacent over opposite. So 1 over 1, which is just 1. Good? Okay, so hang in there. Got another special triangle for... Okay, so the next triangle I want to look at is an equilateral triangle. From this triangle, we get our other special triangle. Now, equilateral. Equa means equal. Lateral means sides. So that means all sides are the same. And if it's equilateral, it's also equal angular, which means all angles have the same measurement. And in any triangle, how many degrees do you have? Good, 180 degrees. So if it's equal angular, that means each angle measures 60 degrees. Agreed? Now, here's what we're going to do. I am going to, and it doesn't matter from which angle I look at since they're all the same, but I'm just going to work with the top angle. From the top angle, I'm going to draw a perpendicular to the base. And that means, since it's perpendicular, I just created a right angle there. Did I not? And if I created a right angle, this line that I drew wasn't just a perpendicular that I drew what's called a perpendicular bisector. And a bisector is going to cut this angle in half. At the same time, it's creating a perpendicular down here. Good? Which means now each side of this line is a 30-degree angle. Are you with me? Okay, so here's the deal. Let me redraw this triangle over here a little bit bigger, a little bit easier to see. I know my 60-degree angle is here. Here's the 30-degree angle we just created, right? By dropping that perpendicular bisector. Now, here's the deal. If I bisect the bottom here, that means I cut this side in half, don't I? So, we could make these sides any number we want. They could each be 5, they could each be 10, they could each be 20, whatever floated our boat. But for simplicity's sake, if we made each side have a value of 1, that means this entire bottom side would have a value of 1, wouldn't it? Okay, 1's easy to deal with. But now that means that each of these sides, now that you've cut it in half, that has a value of 1/2. And now I've given myself a fraction to deal with, which is not what I want to do. With me? If I make all three sides a 1, and I've bisected the bottom here as well, that means each of these two pieces on the bottom is equal to 1/2. Well, I don't want to deal with a fraction. So here's what we do to make our life a little bit simpler. We decide each side of this equilateral triangle is a 2. And when we make each of these three sides a 2, when I cut this in half, this bottom is now a value of 1. Because now this is half of the 2. With me? And if I take a look, the hypotenuse is a 2 because this side has a value of 2. And this is half of it, right? Are you with me? So we're creating our 30 degree, 60 degree, 90 degree triangle from this equilateral triangle. We cut it in half, and this is how we end up with a 2 on the hypotenuse and a 1 on the denominator, is because we were trying to make our life easy when we cut this into 2 separate triangles. I did not want a fraction down here. I wanted a whole number, which means I had to make each side a 2, so half of the bottom could be a 1. Now, the only piece that's missing, the only piece that's missing is this side, isn't it? So, Pythagorean's theorem once again. We have a squared plus 1 squared equals 2 squared. You have a squared plus 1 equals 4. A squared equaling 3. And a has to be the square root of 3. Now, it could have been a plus or minus, and it doesn't really matter which one. But since they didn't tell me anything different, I'm going to say this side is a positive square root of 3. Cool? Okay, so now check it out. I've got my 30, 60, 90 degree triangle. The hypotenuse is always a 2. The side opposite the smallest angle is a 1, because 1 is half of 2, with me. And the side opposite the 60 is a square root of 3. Let me explain a little bit differently. I got 3 different measurements, don't I? 3 different angles, I should say. The side opposite of 30 degrees should be the smallest side. The side opposite the 90 degree should be the largest side. The side opposite the 60 degrees should be somewhere in the middle of these two. 30 degrees, smallest angle. 1 is opposite, smallest side measurement. 90 degrees is largest. Opposite is 2, which should be the largest side measurement. 60 degrees is in between. Square root of 3 should be in between the 1 and the 2. And it is. It's like 1.7, so it's somewhere in between them, which is perfect. Now, we can look at our trig functions. But you know, the interesting thing is this. Since I have a 30 degree and a 60 degree, how many trig functions do you think we're going to look at? Yeah, I've got 12 trig functions to look at for this particular triangle. And you're like, 12? Yep. Watch. The last triangle, the 45, 45, 90 degree triangle, the 45s were the same, so nothing changed. But here, one's a 30 degree and another one's a 60 degree. That's going to change. So, let's look at the cosine of a 30 degree angle, shall we? Remember, cosine is adjacent over hypotenuse. So, here is my 30 degree angle. Adjacent is square root of 3. Opposite is 2. Good? Okay. Let's look at the sine of a 30 degree angle. Sine is, that's right, opposite over hypotenuse. So that's 1 over 2. With me? Let's look at tangent. Tangent of a 30 degree angle. Tangent is opposite over adjacent. So 1 over square root of 3. You allowed to leave that square root in the denominator? Nope. You have to rationalize it. And after you rationalize it, you'll get square root of 3 over 3. So far, so good? All right. Now, let's look at the reciprocals of these 3 trig functions. What's the reciprocal of cosine? Good. The reciprocal of cosine is secant. So secant of 30 degrees. Cosine was 3 over root 2. Pardon me. Square root of 3 over 2. So now I got to go 2 over square root of 3. And yep, we're going to have to rationalize. After you rationalize, you get this lovely number. 2 square root of 3 over 3. Sine. What's the reciprocal of sine? That's right, cosecant. Sine was opposite over hypotenuse. So cosecant is hypotenuse over opposite, which in this case will just be a 2. And last but not least, let's look at tangent. That's cotangent, right? Tangent is opposite over adjacent. That means cotangent is adjacent over opposite, which is the square root of 3 over 1, which would just be square root of 3. Good? Okay. Now, we have a 60-degree angle to look at. Let's look at the cosine of a 60-degree angle. So this is the one I'm now looking at. Cosine, adjacent over hypotenuse. Sine of a 60-degree angle, opposite over hypotenuse. Tangent of a 60-degree angle. Tangent is opposite over adjacent. Cool? Okay. So, what's the reciprocal of cosine? That's right. So the secant of a 60-degree angle. Yeah, flip it over. This would just be 2, wouldn't it? Cosecant of a 60-degree angle. Flip sine over, right? So 2 over square root of 3, which is equal to 2 square root of 3 over 3 after you rationalize it, right? And then cotangent. Yeah, I've got to flip over the square root of 3, which is 1 over square root of 3, which when you rationalize it is square root of 3 over 3. Here's the deal. This 30, 60, 90 degree triangle has a 30-degree angle, which has its own 6 trig functions. It also has a 60-degree angle, which has its own 6 trig functions. You have to be very careful, because if you notice, the cosine of the 60 is exactly the same as the cosine of the 30. It's very easy to get these confused if you don't draw this triangle correctly. Trust me, I'm not suggesting you memorize these. What I'm suggesting is you learn how to write this triangle, just like you should learn how to write the 45, 45, 90-degree triangle. Know how to set those up, and then you'll be able to get all these trig functions. Cool? Okay, hang in there. We're going to go back to that unit circle. Okay, so let's go back to this unit circle. Remember, when we hear the word unit, it means 1. And when we're talking about a unit circle, we're talking about the radius being equal to 1. So here's the thing. My circle I drew on the grid system, the center is at the origin, which is 0, 0, which means it has a radius of 1, since it's a unit circle, which means from the center to this point on the circle has a distance of how much? Yeah, 1, because that's the radius, right? And since I put it on the grid system, this is literally the point 1, 0, isn't it? Okay, and this point up here on the circle, again, if I go from the center to this point on the circle, that's its radius as well, isn't it? And that means it has a point of, good, 0, 1. And if I look over here at this point of the circle, that's its radius also, which means Good, -1, 0. And last but not least, down here, you're getting the hang of it, 0, -1. Got it? Now, remember something that we spoke about just a few minutes ago. This measurement has a measurement of 0 degrees, doesn't it? This one has a measurement, this angle up here has a measurement of 90 degrees. And this has an angle measurement of 180 degrees. And this one's 270 degrees. And then back to 360 degrees, right? Because all of these are 90-degree angles. From here to here and then all the way around. Do you agree? Okay. Now, I could ask us to find the cosine of a 90-degree angle. Since I'm on this grid system, am I thinking adjacent, opposite, and hypotenuse? Or am I thinking x, y's, and r's? Good. X's and r's. And y's. Excuse me. X, y's, and r's. Cosine is x over r, isn't it? But since r is equal to 1, cosine is just x. Agreed? Which means my x coordinate at 90 degrees has a value of 0. With me? Okay. Let's look at the sine of 270 degrees. Again, I'm thinking x, y's, and r's. Correct? Sine is y over r. But since the r is 1, sine is just y. Yes? What is the y coordinate at this 270-degree angle? Yeah, it's equal to -1. Got it? Okay. Let's look at the tangent of 180 degrees. Tangent is y over x. No r in there, so I have to do y over x. Well, at 180 degrees, what's my y value? Good, 0. What's my x value? Good, -1, which would give me a 0 measurement for tangent of 180 degrees. Got it? Okay. How about cotangent of 0 degrees? 0 degrees. Cotangent is the reciprocal of tangent. If tangent is y over x, cotangent is x over y, isn't it? So at 0 degrees, my x value is 1. My y value is 0. Uh-oh. 1 divided by 0. This is undefined. So be it. Cool? Okay. Remember something. I can also go backwards. I could ask us to find the sine of a -90-degree angle, which means I'm starting at 0 degrees, and now I'm going in the clockwise direction. I'm going against the labeling of these quadrants. So this would also be the -90 degrees, wouldn't it? Sine is y. So the y value here would be -1. I could ask for the sine of a -270 degrees, which means here's -90, here's -180, here's your -270, isn't it? Sine is the y value again. Well, that's a 1. Ah, yes, but remember we had those other measurements beside degrees. Yep. If I ask you for the cosine of pi over 3 pi over 2, you had to remember which mark that is. So remember, this one is 0 radians. This one is pi over 2 radians. This one is pi radians. Here's your 3 pi over 2 radians, and then back to 2 pi. So 3 pi over 2, I want the cosine. That's just x, which in this case is 0. With me? Okay, so here's the deal with trig. Know how to draw your 45, 45, 90 degree triangle. Know how to draw your 30, 60, 90 degree triangle. Know how to draw this unit circle. By the way, when I say draw those two triangles and this unit circle, I don't mean just draw them. I mean know how to label them also. Because when you know how to label those three, then you can find any of those trig functions that they ask you for. You don't have to memorize them. You can find them very easily. Cool? Okay, stay tuned. We're going to be talking about reference angle. Okay, so let's talk about that reference angle. Reference angles are based on the x-axis only. I cannot stress that enough. Reference angles are always based off the x-axis. Always, 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 always. I cannot stress that enough. So, I'm only going to label my x-axis. And I'm going to label them in degrees, and I'm going to go in the positive direction. So this is 0 degrees. This is 180 degrees. Now, we've had two triangles besides the unit circle that we are going to be working with on a regular basis. We have our 45, 45, 90 degree triangle, and we have our 30, 60, 90 degree triangle. So, the 45 degree angle, the 30 degree angle, and the 60 degree angle are all first quadrant angles, aren't they? Because all three of those are less than 90 degrees, aren't they? The smallest of the three is 30 degrees. Agreed? So, I'm going to draw my 30 degree angle here. And I'm going to label 30 over here because it's just going to make things a little bit easier for us as opposed to putting it right there. Now, here's something I need you to understand. We're like, when we draw this, we're like, oh yeah, that's easy. That's where 30 is. But I need you to understand something. Because remember when we spoke back in a previous lecture about the initial side of an angle? So this x-axis is the initial side of the angle. And since it's opening in this particular direction, that means it's a positive direction. And it's a positive direction of 30 degrees. Which technically means I took this initial side, which was at 0 degrees. I added 30 degrees, and this is how I ended up at my 30 degree angle. Technically, that's what that means. And you're like, why are you telling me this? Because I dare to say this 30 degree angle is also located in these other three quadrants, but under a different name. And we got to find that different name. Got it? Now, like, how do you find it? We find the other names of this 30 degree angle by using it as a reference angle. So here's something I'm going to say, and I need you to write it down. Reference angles always have the measurement between 0 and 90 degrees. Reference angles always have the measurement between 0 and 90 degrees. Between them. Not 0, not 90, but in between them. Reference angles are always angles that are considered first quadrant angles. That's extremely important. Okay, so now, I say 30 degrees is also located in quadrant 2. I need to find its name. And I'm going to find its name by using 30 degrees as a reference angle. So here's the deal. Reference angles are based on the x-axis, which means from the x-axis I'm going into quadrant 2. Now when I go in the clockwise direction, when I go in the direction that goes against the labeling, that's a negative direction, isn't it? And I'm going negative 30 degrees because I'm trying to find the name of this 30-degree angle. So the way I'm going to find that name is I started at the x-axis, didn't I? Which is 180 degrees. I went in the negative direction, 30 degrees. So I have 180 degrees minus 30 degrees, which is 150 degrees. With me? Okay. But I also want to know what this 30-degree angle's name is in quadrant 3, which means the only way to find it is to use 30 degrees, since that's the thing I'm trying to find another name for. I'm going to use 30 degrees as a reference angle, which is based on the x-axis. So the x-axis closest to quadrant 3 is this x-axis, and I'm going into quadrant 3. And when I go in the direction of the labeling of the quadrants, when I go counterclockwise, that's the positive direction, and I'm going by 30 degrees. So now I started at the x-axis, which was 180 degrees. I went in the positive direction, 30 degrees, which lands me at 210 degrees. Cool? Okay. I have one more quadrant. I have quadrant 4. I need to find the name of this 30-degree angle in quadrant 4. So I'm using 30 degrees as the reference angle off of the x-axis. So from this x-axis, I'm going into quadrant 4, which means when I go clockwise, when I go against the labeling of these quadrants, I'm going in the negative direction, and I'm going in the negative direction by 30 degrees, which means, yeah, I'm not looking at 0 degrees anymore. I'm looking at 360 degrees, because that's also where the circle ends. So 360 degrees minus 30 degrees, 330 degrees. Cool? Okay. 30 degrees is quadrant 1. Now I found the name of 30 degrees in these other 3 quadrants. Now I know what other names 30 degrees goes by. And you're like, well, why is that important? Here's why that's important. Let me give you a quick example just so you kind of understand why I need to know the other names of 30 degrees. Okay? Let's say I want to find the cosine of 210 degrees. Well, I know 210 degrees was found by using this 30-degree angle as a reference angle, which means I can draw my 30, 60, 90-degree triangle. Let's label it. Smallest side, smallest angle, across from it is the smallest side. That was the value of 1, wasn't it? Largest angle, across from it's the hypotenuse, which is the largest side, which has a value of 2. 60 degrees was the one in the middle, so square root of 3. Now help me out. I'm going to sidetrack you. Since I'm looking for cosine, what was the cosine of 30 degrees? Cosine is adjacent over hypotenuse, so square root of 3 over 2. Agreed? Well, since 210 degrees is basically a 30-degree angle, this should also be square root of 3 over 2, shouldn't it? However, this is in quadrant 3. And cosine deals with x's, don't they? And in quadrant 3, x is negative. The reason why it's important to know the names of this 30 degree in the other three quadrants is because if I recognize the angle as a 30-degree angle, I can go to my triangle. I can find, in this case, the cosine of it, and then I just got to figure out if the answer is positive or negative based on the quadrant it is in. With me? Okay. Now, let's look at the 45-degree angle. I'm going in the positive direction by 45 degrees. So 0 plus 45 degrees is 45 degrees, isn't it? Okay. But again, I say this angle has a measurement in quadrant 2. It's known by another name in quadrant 2. So, in order to find its other name, we have to use the reference angle. So we used to have 45 degrees. We need to use 45 degrees as a reference angle. And it's based on the x-axis. So since I want to be in quadrant 2, this is the closest x-axis. So I'm going in this direction. And I'm going in that direction, which is a negative direction, by 45 degrees. So my x-axis had a measurement of how much? 180 degrees. So 180 degrees minus that 45 degrees is, good, 135 degrees. So the name of 45-degree angle, the name of that 45-degree angle in quadrant 2 is known as 135 degrees. That's its name. Got it? Okay. But I also want to know its name in quadrant 3. This is the closest x-axis. I'm going in this direction, which is the positive direction, and I'm going positive by 45 degrees because I want to know the name of 45 degrees. That's why I'm using it. So, the x-axis has a measurement of 180 degrees. Plus the 45 degrees. That's right. This is a 225-degree angle. One more quadrant. Yep. From the x-axis. And since I'm trying to find the quadrant 4 name, right, I'm going to use 360 degrees to help me out. So I'm going in the negative direction by 45 degrees. So 360, because I want to be in quadrant 4, minus 45 degrees. Good, 315 degrees. Got it? One more angle. Yeah. You know what that one more angle is? Yeah, that one more angle is our 60-degree angle. So now I'm going from 0 degrees in the positive direction by 60 degrees, which is a 60-degree angle. So see if you follow along with me when I come up with the names for 60 degrees in these other three quadrants. You do your work, I'll do mine. Hopefully we mesh. Okay, so for quadrant 2, I'm going to go off of the x-axis closest to quadrant 2. I'm going in a negative direction by 60 degrees. So 180 degrees minus 60 degrees. Yep, that's a 120-degree angle. I want to find the name for 60 degrees in quadrant 3. Closest x-axis is the 180. This direction I went is the positive direction because I'm going with the direction of the labeling. That's 60 degrees, right? So 180 degrees plus 60 degrees is a 240-degree angle. And last but not least, quadrant 4, I'm going from the closest x-axis and now I'm going against the labeling. So minus 60 degrees So since I want quadrant 4, I'm doing 360 degrees minus 60 degrees. This is a 300-degree angle. Good? Yeah. You know, this is how they come up with that circle that I'm sure most of you have probably Googled, even printed out, maybe even have in your notebooks. But this is how they come up with it. They come up with it based upon a reference angle. Either a 30-degree, a 45-degree, or a 60-degree reference angle. Are you with me? Now, mind you, this isn't limited to just degrees. It's also for radians. So, we are going to look at this in radian measurement. So, I'm erasing the degrees off the x-axis, and I'm going in radian measurement now. So, 0 radians and 2 pi. And this one is pi, isn't it? Okay. Now, you know, you're going to need to do some converting. 30 degrees, if you convert it to radians, turns out to be pi over 6. So you do your converting, you'll find that's pi over 6. Got it? Okay. Over here, if I want to find the name of pi over 6 in quadrant 2, I am going to use the reference angle. And I'm going to go in the negative direction by pi over 6. Right? So, I need to take pi and subtract pi over 6, don't I? Okay. This is just fractions. Don't get too bogged down. Pi minus pi over 6, correct? Isn't that 1 pi minus 1 pi over 6? Couldn't you think of this if you factor out the pi as 1 minus 1 over 6? You know how to subtract 1 minus 1/6 pretty quickly, I would think. So isn't that pi times 5 over 6? That means this is 5 pi over 6. Cool? Here's the deal. I do the exact same thing, except unfortunately, most of you are saying unfortunately. Unfortunately, I'm going to have to deal with fractions. But if I can just ignore the pi's, factor them out, I can easily do 1 minus 1 over 6. That's a pretty simple subtraction with fractions for us by now. Okay? Okay. Now, I want to go quadrant 3, which means I'm going in the positive direction by pi over 6. So now I have to take pi, which is the x-axis, angle measurement, add pi over 6. So if I add these, what do you get? Yeah, you get 7 pi over 6 now. With me? Okay, let's do quadrant 4. And I'm going in the negative direction by pi over 6. So now I have to take 2 pi and subtract 1 pi over 6, which means I'm taking 2 minus 1 over 6. Okay, you do your subtraction. I get 11 pi over 6. Remember, we basically factored out the pi, so we could just do 2 minus 1 over 6. Good? Okay. Yep, we have 2 other angles to work with. Now, I know some of you in high school had to memorize all this. So you're like, I've got it all memorized. Well, that's great. But sometimes we deal with other angles that are not these standard angles, shall I say. And you're still going to have to know how to deal with the reference angles and when to add and when to subtract. So please make sure you remember how to do this. So we're going to go through these other two as well to make sure everybody's on the same page. Good? Okay, now, when you convert 45 degrees to radians, you get pi over 4. So, I'm going in the positive direction by pi over 4. And this one was the positive direction by pi over 6. Okay. So now I'm adding pi over 4. Or pardon me. That's the negative direction. See, this is why I need you guys to work it with me. Okay. Okay. Negative direction. So now I'm doing pi, 1 pi minus 1/4 pi. So what's 1 minus 1/4? Yeah, 3/4. That makes this 3 pi over 4. And if you got to do your work, do your work. If you need to do side work down here, then do your side work down here. Okay? Don't be shy about having that scratch paper and doing it. Some of you can do it in your head, and some of you are like, I need to do it. Write it down. Then write it down. Pi minus 1 pi over 4. It's basically 1 minus 1/4, isn't it? That's how we got 3/4. Cool? Okay. To get into quadrant 3, I'm going to have to add that pi over 4, aren't I? So what's 1 pi plus 1/4 pi? Yep, 5 pi over 4. And over here, I got to subtract that pi over 4. So now I am doing 2 pi minus 1 pi over 4. So what's 2 minus 1/4? Yep, I think I heard some of you say it. That's 7 pi over 4. Good? Okay, one more. 60 degrees. Convert it to radians. Go ahead. I'll give you a few moments because that'll give me time to erase some of this stuff. Did you get it yet? Got your conversion? Remember, the conversion is pi is equal to 180 degrees. Okay, pi over 3. So, little side note, 6's and 3's go together. 30 degrees means it's pi over 6. 60 degrees means it's pi over 3. And then the 4's go together. 45 pi over, anyway. You'll come up with your own techniques to remember things. Okay, so going in the negative direction by pi over 3. 1 pi minus 1 pi over 3. Yep, 2 pi over 3. Going in the positive direction by pi over 3. 1 pi plus 1 pi over 3. Yep, 4 pi over 3. And last but not least, I'm going in the negative direction by pi over 3. So what's 2 minus 1/3? Yep, 5 pi over 3. These are how we come up with, this is how they came up with that circle that you see online that most people just print out. This is how it's derived based upon reference angles. Are you with me? And I gave you an example after we did the 30 degrees of why it's important that we know how to do this. It's very important you know how to work with reference angles. Cool? Okay, so hang in there. I got a couple of examples for us. Okay, so let's look at these particular examples. Let's look at the first one. By the way, let me go back to the directions. The directions say to find the exact value. That means no calculator. So those of you with your calculators, put them away. So, number 1 wants us to find the cosine of 2 pi over 3. So here's what we need to understand. We need to know what 2 pi over 3, what angle that is. Because if they tell me don't use a calculator, That means it must be one of those angles that we just spoke about a few minutes ago. So, sometimes people are like, well, how do you figure this out? How do you figure out where 2 pi over 3 is? How do you figure this stuff out? So 2 pi over 3 is in radians, agreed? So I need to think radians. So I know this is 0. I know this is pi over 2. I know this is pi. I know this is 3 pi over 2. And this is 2 pi. Agreed? Since this has a denominator of 3, I am going to rewrite pi with a denominator of 3. Wouldn't this be 3 pi over 3? Isn't that equivalent to pi? Yes. So I know that 2 pi over 3 is in here somewhere, right? Okay. So now I got to figure out which quadrant 2 pi over 3 is in. Would it be first quadrant or would it be second quadrant? So, something else to consider. Notice the denominator of 3. Don't we have a 1 pi over 3? 1 pi over 3 was over here in this quadrant, wasn't it? That means 2 pi over 3 has to be in this quadrant. And you're like, well, how do you know that? If you go back and kind of look at the chart that we did, every quadrant has a pi over 3 in it. Every quadrant has a single pi over 3 in it. You will not find within the same quadrant 2 angles with the exact same denominator. So if 1 pi over 3 is in first quadrant, 2 pi over 3 cannot be in first quadrant also. That's not how that works. If you go back and look at that chart we made, each quadrant has an angle with a denominator of 3. So if 1 pi over 3 I already know is in first quadrant, then 2 pi over 3 has got to be in second quadrant. Cool? Okay, so here's where we're going to work out what the reference angle is, right? The reference angle we just figured out. From here to here, we had to subtract pi over 3 to get from 3 pi over 3 to 2 pi over 3. My reference angle is pi over 3. Pi over 3 is equivalent to how many degrees? Good. That's a 60-degree angle. So some people like to know that because it helps their brains put things together. So check this out. Okay? I am talking about a triangle that is in quadrant 2. From here to here is 2 pi over 3. With me? And here, that was my reference angle of pi over 3, wasn't it? Or 60 degrees, right? Which means up here would be 30 degrees, wouldn't it? So now you've got to label your triangle. Across, and here's your right angle. Again, just to make sure before we start labeling. The angle was 2 pi over 3, which means from the start, the initial side of the angle, over to here is 2 pi over 3, which means this distance was pi over 3, which is a 60-degree angle, which means that's a 30-degree angle. Agreed? Okay, so let me get this 2 pi over 3 out of our way since we labeled it here. Across from 30 degrees is a side measurement of, good, 1. Across from the 90-degree angle, the hypotenuse, or the radius as the case is, if you drew a circle around this, is 2. Across from the 60 degrees is square root of 3, isn't it? Now I've got to be careful because this triangle is drawn in the second quadrant. And in the second quadrant, this x value is negative, isn't it? This y value is positive. The radius, always positive. Got it? Okay. So since I'm looking for the cosine, that is going to be your x over your r, isn't it? Well, x is -1, correct? R is 2, so -1/2. Cool? Okay. This is how you put a triangle onto the grid system. So you can see which numbers are actually supposed to be negative. So you can see where the angle actually starts and ends. So you can see the reference angle that's actually happening. So you can draw the triangle correctly. Got it? Okay. Let's look at number 2. Number 2 is asking you for the tangent of 6 pi. You're like, 6 pi? We don't have a 6 pi on here. You're right, we don't have a 6 pi over here, on here at all. But if we take a look, we know from 0 all the way around is 2 pi. Agreed? If I make another turn around the circle, that would be 4 pi, wouldn't it? If I make one more turn around the circle, that would be 6 pi, wouldn't it? So 6 pi would end up right here in the same place that 2 pi is at, in the same place that 0 is at, isn't it? 6 pi is this boundary line, this x-axis. And what's the coordinate here? Yep, 1, 0. 6 pi is actually this positive side of the x-axis, which means I need to look at this coordinate. Got it? For number 2, they wanted 6 pi. That's the angle measurement they wanted. So that's right back here at 2 pi because that was 3 full turns around the circle. Tangent is your y over your x. Y is 0. X is 1, which means the tangent here would be 0 for number 2. Cool? Okay. Let's look at number 3. This problem is very easy for us to work on as well. We just need to know what the sine of 90 is, so we get 90 degrees, so we can multiply by 4. We need to know what the tangent of 180 degrees is, so we can multiply it by 3. Got it? Okay, 90 degrees. Where is 90 degrees on this grid system? Yeah, it's up here, isn't it? Which means I'm looking at the point 0, 1, aren't I? So, 4 times sine is your y. So that would be a 1. (180 degrees), where is that? Yep, that's right here at pi. And that's the coordinate -1, 0, isn't it? Tangent, as we just saw, is y over x. So the y is 0, the x is -1. So I know I get 4 here minus 0 over -1. Yep, 0. So I just get an answer of 4. Cool? These 3 examples are very good examples of how you start using the triangles on the XY axis, how you have to look and see, wow, that's 6 pi. So what does that mean? Oh, that means I'm going around the circle 3 full times in this case. Oh, multiplication. Okay, so I need to figure out the sine at 90 degrees. Well, since that's actually a boundary line, I have to think of the point. Since 180 degrees is actually the boundary line, the axis itself, I have to think of the point. Cool? Okay, so you have fun with this stuff, and I'll catch you on the